Welcome back, everyone. In today's explainer, we are completely demystifying the physics happening right under our noses and, well, sometimes right at our fingertips. We're talking about electric charges and fields. These are the invisible rules of our world, the fundamental forces that hold molecules together, shape our physical reality, and, occasionally give us a tiny jolt when we least expect it. Okay, let's dive into this. Here's our roadmap for today. We're going to start with section 1, the spark of static. Then we'll cover 2, the rules of attraction, 3, properties of charge, 4, measuring the invisible force, and finally, 5, superposition, forces combined. So, part 1, the spark of static. I want you to think about your everyday sensory experiences for a second. We've literally all been there, right? You're taking off a synthetic sweater on a cold, dry day, and you hear that distinct crackle. Or maybe you slide across a car seat and just zap. You get a sharp little shock when you touch the metal door handle. And on a much, much grander scale, you look up during a thunderstorm and see a massive bolt of lightning just split the sky. So what do all these things have in common? Well, they're all examples of electric discharge. Charges have accumulated on insulating surfaces just from rubbing together, and then they suddenly discharge through your body, or in the case of lightning, right through the air. Which actually brings us to a super important definition for this whole explainer, electrostatics. When we say static, we just mean anything that doesn't move or change with time. So electrostatics is precisely the study of forces, fields, and potentials that arise from these static, stationary charges. This is literally the foundation we're building everything on today. Moving right along to part 2, the rules of attraction. This story actually starts way back around 600 BC in Greece with a guy named Thales of Miletus. He noticed that if you rubbed amber with wool or silk, it would suddenly attract really light objects like little bits of straw. Fun fact here, the actual word electricity comes directly from the Greek word electron, which literally just means amber. Pretty cool, right? Then you jump forward to the 18th century, and the American scientist Benjamin Franklin gave names to the 2 kinds of charges we observe, calling them positive and negative. And by 1785, Charles Coulomb figured out the exact mathematical law of force between them. So, through years of really careful experiments, rubbing glass rods, plastic rods, silk, cat's fur, the whole shebang, scientists realized a fundamental rule. Like charges repel and unlike charges attract. It's that simple. This differentiating property is what we call the polarity of charge. But here is the fascinating part that Benjamin Franklin noticed. If you rub a glass rod with silk, they acquire opposite charges, right? So they attract each other. But if you bring that electrified glass rod back into physical contact with the exact same piece of silk it was rubbed against, they don't attract or repel anymore. They neutralize or totally nullify each other perfectly. This is exactly why Franklin assigned them mathematical signs of positive and negative, because when you add equal opposites together, you get 0. But that begs the question, why do some things hold a charge while others just don't? Well, it all comes down to conductors versus insulators. Conductors, think metals, the earth, and, yep, our own human bodies, have electrons that are comparatively free to move around inside the material. Insulators, on the other hand, like glass, plastic, or wood, offer really high resistance to the passage of electricity. If you put a charge on an insulator, it stays put. This perfectly explains why you can electrify a plastic comb just by rubbing it on dry hair, but if you try rubbing a metal spoon in your bare hand, absolutely nothing happens. Why? Because the metal spoon is a conductor, and you are a conductor, so the charges just leak right through your hand, down your body, and straight into the ground. All right, section 3, 3 properties of charge. Now, what's really interesting here is how we can break down the anatomy of a charge into 3 distinct properties. First up, we have additivity. If a system contains multiple point charges, you just add them up algebraically like normal, real numbers, making sure to keep their positive and negative signs. Second, we have conservation. When you rub that glass rod with silk, you aren't creating new charges out of thin air, no way. You're simply transferring existing electrons from the rod to the silk. The total charge of an isolated system is always conserved. And third, quantization. This basically means charge isn't some continuous fluid that you can just divide up infinitely. It comes in discrete, indivisible little packets. All free charges are integral multiples of a basic unit, which we denote with a lowercase e. To really wrap our heads around quantization, the source material provides this brilliant analogy. The dotted line. Think about it. If you draw a dotted line on a piece of paper and hold it right up to your eye, you see the individual dots, right? The distinct, separate steps. But if you tape that paper to the wall and walk all the way across the room, it looks like one solid continuous line. Charge works exactly the same way. Down at the microscopic scale, we can see the dots, the individual charges. But at our macroscopic, everyday scale, where we deal with just enormous amounts of charge all at once, it appears completely continuous. So just how small is that individual dot? Well, the basic unit of charge carried by a single electron or proton is E, and it equals 1.602192 times 10 to the power of negative 19 coulombs. I mean, that is a staggeringly tiny number. And by the way, the Coulomb, denoted by a capital C, is the standard SI unit of charge. And this brilliantly illustrates just how incredibly microscopic the charge of a single electron really is. Just to put that into perspective for you, if you had a body that gave out 1 billion electrons every single second, it would still take you roughly 200 years to accumulate just one single coulomb of total charge. Isn't that wild? That is exactly why in everyday, practical electrostatics, we rarely use whole coulombs. We use microcoulombs or millicoulombs instead. Let's shift gears to section 4, measuring the invisible force. Now that we actually know what a charge is, how on earth do we measure the push and pull between them? Well, enter Charles-Augustin de Coulomb. He was a French physicist and military engineer. Back in 1785, he invented this highly sensitive device called a torsion balance, and he used it to measure the incredibly feeble forces of electric attraction and repulsion between these tiny, charged metallic spheres. What Coulomb discovered is this incredibly elegant mathematical relationship that we now call Coulomb's Law. He basically found that the force between two-point charges drops off super fast as they get further apart. Specifically, it varies inversely as the square of their distance. And on the flip side, the force gets stronger in direct proportion to the product of the magnitude of the two charges. But you know what's truly incredible? Coulomb figured out this entire mathematical ratio without even knowing the explicit magnitude of the charge he was measuring to begin with. Seriously, he just started with a charged sphere, touched it to an identical uncharged sphere to perfectly have the charge, and just mapped out all the mathematical ratios from there. A real game changer. Now, to really give you a sense of scale, let's compare the electric force to a force we are all very, very familiar with: gravity. If you take two protons inside a nucleus separated by an unimaginably tiny distance, the electric force of repulsion is about 230 newtons. But the gravitational force of attraction between their masses at that exact same distance, it's 1.9 times 10 to the negative 34 newtons. So the absolute crucial takeaway here is this: the electric force is 1.3 times 10 to the 36 times stronger than the gravitational force. I mean, it's a number so large it practically defies human comprehension. Electric forces are just enormously, unbelievably stronger than gravity. Okay, finally, section 5, superposition, forces combined. Let's see how all of this builds when we introduce a few more players to the game. Coulomb's law is perfect for two charges hanging out in a vacuum. But what if you have 3 or 4 or literally a million charges all interacting at the exact same time? Well, experimentally, scientists verified something called the principle of superposition. It simply states that the total force on a single charge is the vector sum of all the individual forces acting upon it. And honestly, here is the beautiful, reassuring part of this whole thing. The individual forces between any two charges are completely unaffected by the presence of all the other charges buzzing around them. They just quietly do their own mathematical thing, and you simply add them all up to see exactly where the charge is ultimately going to be pushed or pulled. So, we've seen today that all matter is made up of atoms containing precisely balanced positive and negative charges. The forces that hold your molecules together, the forces that give an object surface tension, the very forces that prevent your hand from just passing straight through the table you're resting it on, they are all, at their core, entirely electrical in nature. So I'll leave you with this mind-bending thought. If electrical forces are 10 to the power of 36 times stronger than gravity, what incredible, invisible architecture is secretly holding you and the entire physical universe together at this very second? Thank you so much for joining me on this explainer, and keep questioning the invisible rules of our world.